It's a pleasure being here. Thanks for the invitation. So I'm going to give more of a survey talk on recent progress on algorithms for maximizing submodular functions, and it's based on joint work with Niv Buchbinder, Moran Feldman, and Roy Schwartz. So since I'm the first speaker, I'll define what is a submodular function. So submodular function is defined over a ground set. It's a set function defined over subsets of the ground set. And if we have two sets A and B, then if F is submodular, then for any A and B, it satisfies that F of the union plus F of the intersection of the two sets is less than or equal to F of A plus F of B. So you can see that it's a stronger property than subadditivity. Another way or more intuitive way of understanding submodularity is through the property of decreasing marginals. And what this says is the following, that if we have two sets A and B, and A is contained in B, and now we take some element which is in either set, and we added to both A and B, then our gain from adding it to A, the smaller set, is at least as big as adding it to B. And monotonicity is standard definition. F is a monotone submodular function. If for any A which is contained in B, F of A is less than or equal to F of B. So let's quickly see an example of coverage of diminishing returns. So we have these elements, and if we have subsets defined over these elements, and the value of a bunch of subsets is the number of points they cover in their union. So let's say we have this set, and now we add this second set, so we gain these three black points. On the other hand, if we already have these two sets, and now we add the former set, then we only gain 2 points. So this is an example of this decreasing marginals. A classic example of submodular functions, which I'll use later on. This comes up in algorithmic game theory. Suppose we have a bunch of items, and these are unsplittable items. Now, we have a bunch of agents, and we want to assign the items to the agents. Now, each agent has his own submodular function, which is defined over subsets of the elements, and it's unique to the agent. Typically, it's a monotone. It doesn't necessarily have to be like that, but typically, it's a monotone submodular function. And the social welfare, given an allocation of the items to the agents, the social welfare is just the sum of the valuations of the agents. And the goal is to assign the items to the agents so as to maximize the social welfare. Submodular functions appear everywhere in combinatorial optimization. Cuts and graph, I'll talk about it further in a few minutes. Cuts and graphs, hypergraphs, rank functions in matroids, coverage function, of course, mutual information. In economics and game theory, we see them all over the place. Optimization. Suppose I have a submodular function f, and I have a family of subsets. So I have my ground set N, and I have a family of allowed subsets from which I can choose my solution. And the goal is to find a subset among capital M, the family of allowed subsets, that maximizes my submodular function, f. Now, how is f given? F is a function which is defined over all subsets. So the typical way that we assume that the function is given is through the value oracle, what's called the value oracle model. And this means that we have a black box that we can probe and get the input to the black box is a subset S. The output is the value of f of S. And a measure for our complexity is the number of such queries that we have. Again, maximizing a submodular function over a family of subsets is, again, a problem that comes up in many applications. I've written here a bunch of them. I won't go into the details. It's very rife now in machine learning, game theory, and economics. Of course, we're all more familiar with the classic applications in combinatorial optimization. Let me start with the first problem that I want to discuss is the unconstrained version. In the unconstrained version, we can pick any subset that we want to, and we want to find the subset that would maximize our submodular function. Now, clearly, this problem is interesting only in the non-monotone version. So I'm going to assume that my function is non-monotone. And so this is our ground set, and we want to find the subset S that maximizes f of S. A classic example is a cut function in an undirected graph. So we have an undirected graph. We have weights on the edges, and given a subset of the vertices, the submodular function is defined by the weight of the edges which go out of the set. This is a submodular. Yeah.
Yeah. What if the graph is directed?
Pardon?
What if the graph was directed? Yeah, here it's not directed, but it could also be directed.
I agree. Sure. But in this example, I'm looking at undirected graphs. Yeah, totally agree. So this is an example of the function. The value of the submodular function is the weight of the edges going out of a subset of the vertices. This is also an example of a symmetric submodular function, because if we have a subset S, then the value of f of S and f of n minus S is clearly the same, which is actually not true in the directed case. And as Yuval pointed out, this also captures the directed case, facility location, some variants of max sub. It captures many other settings. It has been used in various papers. And this problem has come up in various settings and papers in recent years. In terms of history, well, people in operations research have been looking at maximizing submodular functions since the 60s. In terms of upper bounds approximation algorithms, the first algorithm that I'm familiar with for this specific problem is by Feige, Mirokny, and Vondrak from 2007. And they showed that if we just pick a random solution, a random set, then this is going to give us a factor of 1/4, improved to 1/3 using local search, to 0.4 more sophisticated local search, and then there was some small improvements. In terms of hardness, the first group, Feige, Miropny, and Vondrak, also showed an information theoretical upper bound of 1/2. So half is the best that we can achieve if the number of queries to the black box is polynomial. If we want to go beyond 1/2, we need an exponential number of queries. So 1/2 is the best we can hope for. And the question that was open in recent years was whether 1/2 can be achieved. And in a paper from a few years ago, in joint work with Buchbinder, Feldman, and Schwartz, we indeed gave a randomized half approximation algorithm. Now, I mentioned before that max cut is a special case of this problem. Now, for max cut, we know, for example, the work of Gomez and Williamson, we can achieve a factor of 0.878. So how come they can break the factor of 1/2? Just to check your, pardon? Exactly, yeah. It's not given, in the case of max cut, the function is not given as a black box, but it's given through a graph, exactly. Very good, Yuval. Okay. One approach that has been very useful for getting approximation algorithms for some modular functions is greedy algorithm. Now, greedy algorithm is very useful for monotone functions, not so much for pardon?
So what is the hard instance? Because the hard instance can't be max cut because you learn the graph.
No. The instance is you hide a function as a modular function, and you choose a subset, and the value of the submodular function is defined by the intersection for a subset S. The submodular function is defined by the intersection of S with a subset that you chose, that you're hiding there. And it's a bit more complicated than that, and you need an exponential number of, if you only do a polynomial number of probes, then the probability of hitting the hidden subset is very low. This is the high-level idea. So, So the problem with greedy that it fails for non-monotone functions. The basic greedy algorithm starts with an empty set and starts adding elements to it. Another way of looking at the greedy algorithm is start with a full set and then iteratively remove elements from it. Both algorithms don't seem to be working very well for non-monotone functions, but let's do a combination of the two algorithms. So let me yeah.
So is the greedy value for symmetric submodular?
Pardon? Symmetric functions are much easier than for symmetric functions. A half was known before our result. What is the algorithm? It's just a random set gives a half. Okay. Probably the greedy algorithm doesn't work. I don't want to just answer offhand, but probably it doesn't work.
So asking the two views are the same. Like,
Pardon?
the two views that you pointed out, going from here to the whole set, symmetric will be the same.
If that would be the same, depends on your exact. I was talking more high level. I mean, you have to define the exact rule. Okay, so let me graphically explain the algorithm. So we start with two solutions, A and B. The first solution is the empty solution, and here it is. The other solution, B, is the full solution, which contains all the elements. Now, the idea is I want to go through the coordinates, through the elements, one by one, and decide for each coordinate whether I'm taking the one from A or the one from B. At the end of this pass, when I finish going over all coordinates, A and B are going to converge to the same solution, and this is going to be my output. So let's look at the first coordinate. So if I decide to change A's coordinate from a 0 to a 1, that will change the value of my function by delta 1. And similarly, if I want to change the first coordinate of B from 1 to 0, that would change the value of my function by delta 2. Delta 1 and delta 2 can be both, they can be positive or negative. Okay, so I'm going to pick, let's say delta 1 is bigger than delta 2, then I'm going to change A. My gain is bigger. So I'll change the first coordinate of A from 0 to 1. So now both A and B agree on the first coordinate. Now I go to the second coordinate, and I do the same, compare delta 1 and delta 2. Let's say now delta 1 is the smaller one, so I'll move B. So now A and B agree on the first two coordinates. And now the third coordinate, again, delta 1 and delta 2. Let's say delta 1 is bigger than delta 2. So I'm going to move A. And now both of them agree on all three coordinates. And this is my output. So this is the algorithm. It is summarized here in this pseudocode, but I think it's pretty clear. This is a deterministic algorithm, and the claim is that this that this gives a 1/3 approximation for the unconstrained problem. So let's quickly go over the proof. So the first observation is that it follows from submodularity that delta 1 plus delta 2 are always non-negative. So at least one of them is going to be non-negative. I'm guaranteed that. I'll skip the proof of this. Now, to analyze the algorithm, the idea is to follow the evolution of the solution compared with opt. So I have my solution, my initial solution A and B. AI and BI is the solution after I've dealt with the first I coordinates. So AI and BI agree on the first I coordinates. And opt is my real, or opt0, that's my real opt. And opt-I agrees with AI and BI on the first I coordinates. And on the rest of the coordinates, it agrees with opt. So initially, opt0 is just opt, and opt-n is just the output of the algorithm, which is equal to also so opt-n is equal to an and bn. Now, the main observation, the main lemma, I won't prove it here, the proof is not difficult, is that when we fix the ith coordinate, so the change in opt between opt I minus 1 and opt I is f of opt I minus 1 minus f of opt I, and that can be upper bounded by either delta 1 or delta 2, depending on which of the two changes we decided to make. Now, to analyze the algorithm, we just define a potential function. So at the ith step, the potential function is defined to be f of ai plus f of bi plus f of opt I. Now, what's the initial potential? So I'm assuming, I didn't mention, I'm assuming that my function is non-negative. Otherwise, there's no, we cannot talk about approximating it. So, so phi 0 is at least f of opt. Remember, opt 0 is just opt, and the other two terms are non-negative. And phi n is equal to 3 times f of alg of our solution. Now, the lemma that we had on the previous slide that bounded the difference between f of opt I and f of opt I minus 1 essentially says that the potential is non-negative. So if we look at phi I minus 1, and we just plug in, expand it by the definition of the potential function, well, one of ai and, let's say we chose to change ai, then bi and bi minus 1 are equal, and they just cancel each other. And by the previous lemma, we know that f of I minus f of I minus 1 upper bounds the change between f of opt I and opt I minus 1 and f of opt I. So we get that the potential is non-negative. And this means that the final potential, which is 3 times f of alg, is bigger than the initial potential, which is at least f of opt, meaning that f of alg is at least 1/3 of f of opt. And the analysis for this specific algorithm turns out to be tight. Now, remember, I promised you one half, not 1/3. So the idea, if we want to improve on this algorithm, the idea is to do a randomized step. Now, recall, by submodularity, delta 1 plus delta 2 is non-negative. Now, if let's say one of them is, let's say delta 1 is bigger than or equal to 0, while delta 2 is negative, intuitively go for delta 1 and vice versa. But what happens if both delta 1 and delta 2 are positive or non-negative or even equal? What should we do in that case? Well, in the deterministic algorithm, we always went for the bigger of the two. But let's look at the following randomized rule. When both of them are non-negative, we're going to pick a direction at random, but proportionally to the values of delta 1 and delta 2. So the algorithm is, this is the interesting line. If both delta 1 and delta 2 are non-negative, then we'll choose with probability delta 1 over delta 1 plus delta 2. We'll pick A, and with a complementing probability, we'll pick B. Turns out that in expectation, this algorithm is going to give us a half approximation. And from the lower bound example, we remember that this is the best possible result we can achieve. The idea of the analysis, we're going to change slightly the potential function to be, at the ith step, to be f of ai plus f of bi plus twice opt I. Now these are random variables, these values. And initially, we know that phi of 0 is at least twice f of opt, and phi n is 4 times f of alg. We need a new lemma. For the deterministic case, we bounded the difference between opt I and opt I minus 1. This should be f of opt I minus 1 and f of opt I. We bounded it by either delta 1 or delta 2, depending on the move that we did. Here, we bound the expected difference between the two solution by half of the expected difference between the AI and AI minus 1 plus half of the expectation between BI and BI minus 1. So if we believe this lemma, then we get that it yields that the expected difference between the potential function is non-negative, which means that 4 times E expectation of f of alg, which is the expected phi n, is bigger than phi 0, which is bigger than twice f of opt. And this gives us the result that we wanted, that f of opt is at least, f of alg is bigger than or equal to half f of opt. And I won't go into the details of the proof are not complicated. I won't go into them. Okay, so this is our algorithm. In a minute, I'll tell you a bit more about this algorithm. But first, I want to talk about relaxations of submodular functions. So when we do approximation algorithms for linear functions, linear objective functions, the strong tool that we have is a linear relaxation of the problem. If we have, let's say, a variable which is allowed to, in the integral solution, can only take values 0 or 1, when we relax it, we allow it to take any fraction between 0 and 1. What would be the analog relaxation for a submodular function? So the natural notion is the convex, for a minimization problem, the convex closure, and for a maximization problem, the concave closure. Now, these closures are defined by a distribution which, well, the definition is written here. The distribution preserves the marginals. So we have a point x, which is in the hypercube. It's a fractional point. So x is, let's say the coordinates are x1, x2, up to xn. All of them are fractional values. And we want to, and a relaxation has to tell us what is the value of the extension of the submodular function on this fractional point. So the requirement from the distribution is that marginals are preserved, and the extension agrees with the original submodular function on the integral points. Now, it turns out that this is true for any function, for any set function f. Now, for a submodular function, the convex closure has a very simple interpretation. It's called the Lovász extension, And it says the following. Let's fix some value theta between 0 and 1. So some of the coordinates xi are bigger than theta, some are smaller than theta. Let's look at the subset of the elements I such that xi is bigger than or equal to theta. This gives us a subset of the elements. So f of theta is defined to be the value of the function f on that subset of the elements I, for which xi is bigger than or equal to bigger than theta. Now, when we want to define the value of the extension, we just take expectation over all values of theta. And this is for vector x. This expectation is defined to be the extension of the function, of the submodular function f. This is a convex function, and it also has a very nice probabilistic interpretation. Very nice interpretation, a correlated rounding of the elements. Unfortunately, when we do the analog for a maximization problem, so for a maximization problem, we need the concave closure of the function. Unfortunately, maximization problems are, as we know, even the basic one, the unconstrained version, are NP hard, and the concave closure doesn't have a nice structure like we saw before for the convex one. So instead, we're going to use what's called the multilinear extension. Multilinear extension was actually defined, I think, in work in game theory in the 60s, but was brought and used in papers by Jan Vondra, Bob Birokny, or Feige. The multilinear extension is defined as follows. Let us do the following. So in the Lovász extension, we did correlated rounding. In the multilinear extension, we're going to do independent rounding. So we have our point x1 up to xn. Each variable, each element I independently picks himself to be 0 or 1 with probability xi. And now, let's take the expectation of this experiment. So for every subset R in N, the probability of getting R is success on the elements in R and failure on the elements which are not in R. This happens with probability xi. This happens with probability 1 minus xi. We multiply it by the value of the function on the subset R, and now we just take expectation. So capital F denotes the multilinear extension, and it is the value of big F of x is equal to the expectation of this experiment. Now, the function, the multilinear extension, is neither convex nor concave, but it does have some nice properties. For example, it is concave in every positive non-negative direction D in the case of a submodular function. Also, rounding F is very natural, at least in the unconstrained case, and it preserves, of course, expectation. So it has nice properties, and which we're going to use. So just to summarize, we have the concave closure, which is bigger than or equal to the so for a particular vector x, the concave closure is bigger than or equal to the multilinear extension on x, bigger than or equal to the convex closure, which is equal to the Lovász extension. Okay. Now let's go back to our unconstrained algorithm, and let's reinterpret it in the context of the multilinear extension. Now, so let's take our randomized algorithm and make it deterministic, but yielding a fractional solution. And this fractional solution is going to be a half approximation to our original f. So the algorithm is the following. We start with our two solutions, A and B. And now if, let's say, both delta 1 and delta 2 are non-negative, in that case, instead of making a probabilistic choice, we'll just move to a fractional point, alpha, which is equal to delta 1 divided by delta 1 plus delta 2. In the second step, let's say delta 2 is negative. In that case, delta 1 we know is non-negative, so we move all the way to B. In the third step, let's say, again, both delta 1 prime and delta 2 prime are non-negative. So in that case, we'll move to a fractional point. And this fractional point is our final output. And a natural, yeah?
So is this continuous approach equivalent to making the probabilistic choice?
Yeah, I mean, the proof of this algorithm just follows step by step the randomized one, except that here you do it deterministically.
I'm not saying that the proof is, or the algorithms equivalent as well.
What do you mean by the algorithm?
So making the probabilistic choice is just deciding which direction you're going. The continuous is find just a fractional point at the end.
But the randomized algorithm gives you a distribution over solutions, right? So I'm not sure I understand.
After the rounding, you get the same distribution as if you have the rounding.
You mean after the rounding? You mean if?
Of the deterministic one, probably would not get the same distribution.
I don't think so.
So we have to check.
It's a good question. I'm not sure. Okay. Now, a natural question is: we saw a randomized half approximation to the unconstrained maximization problem. The deterministic version of the randomized algorithm only gives 1/3. A very natural and interesting question is, can we get deterministically the factor of half, or can we rule out the possibility of getting a deterministic algorithm which achieves 1/2? It is not, yeah?
We did running this fractional deterministic algorithm.
Yeah, but
we did randomization
for evaluating the multilinear extension. Yeah. So the problem is it is not clear how to de-randomize the randomized algorithm using the method of, for example, using the method of conditional probabilities. This has been an open question in the last two, three years, and very recently, Niv Buchbinder and Moran Feldman showed how to de-randomize the algorithm and achieve a deterministic factor of half. And Niv will talk about this result today in the afternoon. let's move on to constrained problems. So in the constrained submodular maximization problem, we're given a function f, we're given a family of allowed subsets m, and we want to maximize the function f, but we can only choose sets from the family m. A very common way of restricting the allowed family is by constraining the family of sets to be independent sets in a matroid. This is already earlier work from the from the 70s, and even if our function f is monotone, then it already captures submodular welfare, coverage, generalized assignment, etc. Common techniques are greedy local search, and for some instances, this has provided the best possible approximation factors, and even for more general families than matroids, like knapsack constraints, intersection of matroids, what's called K-exchange systems, and more. So in the case of a monotone function, in general, already Fisher, Nemhauser, and Woolsey showed in '78 that the greedy algorithm gives a factor of 1/2. And this was later improved by Kalinesko, Chikouri, Pal, and Vondrak to be not the greedy algorithm, but they gave another algorithm, which I'll present in 2 minutes, which achieves 1 minus 1 over E. And this is actually best possible. Even for a uniform matroid, you cannot get better than 1 minus 1 over E. Again, this was already shown by Nemhauser, Woolsey, Fisher. Okay, for non-monotone functions, the numbers are not as nice. There's the hardness is 0.478, and there's still, I'll talk about this a bit later, but there's still a gap between upper and lower bounds. Okay. So let's look at the basic version. I want to maximize a monotone function f over a modular function f over a matroid. So first we relax the problem. So let's look at the can say following this, the paradigm, what we do when we want to approximate a linear function. So first we look at the polytope which is associated with a matroid, and all the extreme points in this polytope are integral, and we replace our submodular function f by the multilinear function big F. Before showing you how to do, let me go to the end. Suppose we've already found an approximate solution in our polytope. Then using a method called pipage developed originally by Agev and Sviridenko. So Kalinesko et al. Showed that if we have a point in the matroid polytope, then we can also find an integral solution in the polytope. So meaning we can round the fractional solution without losing anything in the objective function. And this is actually true for both monotone and non-monotone functions. So now let's see an algorithm called continuous greedy, which was originally developed by Kalinesco, Chikuri, Pal, and Vondrak in 08. And this algorithm yields an approximate fractional solution for a monotone function. And I'll use the fact that our polytope is downward closed. Okay, so the algorithm is the following. We start at point at the origin, and now we want to start making progress. Question is, in which direction? In the continuous greedy algorithm, we pick a direction y, which maximizes the directional derivative among all feasible vectors y in our polytope. So y is a vector. Y is a vector in our polytope, in our matroid polytope, and among all vectors y, we look for the one that maximizes the directional derivative. So this is an optimization problem, and when our polytope is a matroid, it is very easy to do this optimization problem. We know that the greedy algorithm works. Okay, so we find initially we start at 0. We find the vector y, which maximizes the directional derivative. And let's say this is our vector. So we move an infinitesimal distance in that direction, and we run again. I'm describing the algorithm as a continuous algorithm. And now we repeat that, and we move in this direction. And now we repeat over and over. And at some point, we need to stop. I'll talk about that in a second. But this is the algorithm. And let's say we decided to stop at that point. Okay. So we can think of it as if we are running it over time. So we have t is our time, and it's a continuous variable. And what Kalinesco et al. Showed that if x of t is the value, is our point at time t, then big F, the multilinear extension value of the point x of t, is at least 1 minus e to the minus t of the optimal solution. Now a natural question is, when do we stop the algorithm? Now by definition, the algorithm, any point that the algorithm yields while running is a combination of feasible directions in the polytope. So as long as t is less than or equal to 1, we are guaranteed to have a point inside the polytope. So we can safely stop at t equals 1. And by the above theorem, that would give us a 1 minus 1 over e approximation. And this is true for any monotone function. What happened here? Okay, let's see a quick proof of this. So we want to understand the derivative of, the partial derivative of f with respect to t. Let me just highlight the main, the interesting points. So this is just putting in the definition. So y star is the direction that we picked at time t. And we know that its value, it's at least as good as the optimal solution, which is also a feasible point. And here I'm replacing, I'm using monotonicity, and I'm replacing, and I know that the value of my function at point x of t is at least as good as when taking the max of x and the optimal solution. And I can also get rid of the denominator because of monotonicity. And this step, f is inside the sum when summing up over all indices I. Again, by submodularity, this is better than taking f over the whole vector. And the point is that we get a this gives us, this lower bound gives us a differential equation, and the solution is exactly the relation that I showed you before. So this is the whole continuous proof for this algorithm. Now we know this is optimal because we know that maximizing a monotone submodular function over a matroid is 1 minus 1 over E hard. But is this the end? Is this the end of the story? So first of all, what do we do with a non-monotone function? Second of all, even for a monotone function, let's take the submodular welfare problem that I mentioned in the beginning of the talk. When the number of players k does not go to infinity, then we can get a better bound as a function of k. It's true that this bound goes to 1 minus 1 over E, but for smaller values of k, it's better. Can we achieve this this bound? And in particular, in the case of 2 players, we get we can get 2/3 in this case. Okay, so let's see what change can we make in the continuous greedy algorithm that will help us for the submodular welfare problem, which is monotone, and also for non-monotone functions. So recall, this is the definition of the continuous greedy algorithm. We look for the direction in the polytope that maximizes the directional derivative. Let's make a small change, and let's call it the measured continuous greedy. Measured continuous greedy, instead of maximizing the directional derivative, we also we multiply yi by 1 minus xi of t. And this would mean that the derivative, in the ith direction, instead of growing by y star, it will change by 1 minus xi multiplied by yi. So we're using here extra information, which is the position, the point x of t that we're currently in the case of the multilinear extension, if we look at just single variable, we look at the partial derivative of the ith coordinate, then that's a linear function. So that derivative is fixed. So it does not depend on where we are. And this is the extra information that we're using in the measured continuous greedy. And also, our rate of growth is more bounded. It is multiplied by 1 minus xi of t. Let's see what changes does this small change, what do we gain from it? So the measured continuous greedy for a monotone function, it gives the same result as the continuous greedy. For a non-monotone function, for which the continuous greedy does not seem to give any bound, we can get the value of the solution at time t is t times e to the minus t multiplied by opt. And this means that if we stop at point t, at time what t equals 1, then we get a 1 over e approximation. And as I told you, we get a fractional point, but the pipage technique works for both monotone and non-monotone functions, so we can round the fractional solution into an integral solution. How much more time do I have? 5 minutes. Okay, I won't go over the proof. Let me just show you. Yeah. So let me just show you one more thing. So in principle, when we run the measured continuous greedy, we get the same bound as the continuous greedy, which is 1 minus 1 over e. However, one advantage of the measured continuous greedy is that it makes less progress. It increases slower than the continuous greedy, and we can claim that that if we look at a particular coordinate, then it is bounded by 1 minus e to the minus t. How can we use that fact? Well, in certain instances, it allows us to run beyond time 1 and still remain feasible within the polytope. So let's see an example. The example is the following. We have the submodular max sut problem. So this is the CNF formula. And we have a submodular function f, which if we have a subset of the clauses which are satisfied, then the f tells us what is the value of this subset. And we want to maximize the function f. This turns out to maximizing a monotone submodular function over a partition matroid. Why partition matroid? Well, each xi is replaced by a group of 2 xi, 0, xi, 1, and we have to choose exactly one from each group. And if we define CXV as the clauses satisfied by setting x, the variable x, to be equal to v, then for given a set of clauses S, the function g of s is just the function of the union over all xv in the set S. In terms of defining the function, the submodular function g, we can set a variable to both 0 and 1. The function doesn't care about that. This function is submodular. G is submodular because of the submodularity of f. But x can only be set to either true or false. This will be taken care by the partition matroid. So submodular max set is an instance of a monotone submodular maximization problem over a matroid. And the question is, big T, I want to run the algorithm beyond time 1. So let's look at the variable x, and let's say t0 is the total time in which x comma 0 is increased, and t1 is the total time in which x comma 1 is increased. Well, clearly t0 plus t1 is less than or equal to t. Now, by the properties of the measured greedy, each one of these is upper bounded by this value. Now, we need to have the matroid constraint that x comma 0 plus x comma 1 is less than or equal to 1. Well, we know that they're less than or equal to this value, equal to this. Now, this value is maximized at t over 2. So this means that the matroid's constraints will be satisfied if this value, the sum of x comma 0 and x comma 1, upper bounded by this value from here, this needs to be less than 1. What this means is that t, our time, can go up to instead of 1, to ln 2. And this gives an approximation factor of 3/4 for this problem, submodular max set. Skip this, which turns out to be a special case of submodular welfare. So using the measured continuous greedy and going beyond time equal 1 allows us to get improved results for several problems. I thought I'll have time to talk about randomized greedy versions, which are also applicable to non-monotone functions, not just to monotone functions. I guess I'm running out of time, but Niv will also talk about this related to results in his talk, so you'll hear about it in the afternoon. So I'll stop at this point.
Thank you. We have time for questions.
Yeah.
Can you, in some way, modify this to work in the basis over the basis of the matrix?
No, I need it to be downward closed. And problems become very hard when you work on the basis.
I have a question about the randomization. Do you believe that the continuous greedy can be also de-randomized somehow, or what is your guess?
I don't know.
Is there a gap between what randomized algorithms can achieve?
Maybe there's an indirect way of de-randomizing, not the the maybe not de-randomizing the query, but I don't know, for every problem somehow going around, or not sure.
What are the numbers for 0.478 0.491?
Okay, so this is hardness. Okay, when you want to optimize a non-monotone function over a matroid, then the best you can do is 0.478, and pardon? This is the best approximation you can get. Yeah.
These are like integrality gaps, symmetry gaps.
Yeah.
They're ugly numbers.
So they're not roots of polynomial.
No. Some example is you compute some kind of ratio.
Okay. Thanks again.